For better understanding of phase difference between voltage and current, we have a new way to represent this called as a phasor diagram. We will see how do we represent this. Let's say we have voltage V of t equals to V naught sine of omega t. This can be represented with a rotating arrow mark, somewhat like this, where the length of this arrow represents the amplitude V naught, and this angle with respect to x-axis theta is nothing but omega into t, because for this phasor we can say that omega is the angular velocity, the speed or the angular speed at which it is rotating, that is omega. Then V naught sine of omega t is nothing but this length, where you drop a perpendicular from this onto the y-axis. This represents what? V naught sine of omega t. Right? Now, let's say I have current I of t as I naught into sine of omega t plus 1. What is the meaning of this? That the current is little ahead of the phase by phi. That means the current would be somewhat like this, or the phasor for current would be like this, having a different amplitude. So the length of the phasor would be how much? This is I naught, and this angle is omega t plus phi. So the phase difference between voltage and current is this, which is nothing but phi, right? We are going to represent voltage and current in phases for better understanding of these AC circuits. So for this resistance connected to an AC source, how the phasor diagram would be? We have seen that voltage across the resistor is nothing but the voltage of the source, which is V naught sine of omega t. Whereas current passing through the resistor, IR is equal to V naught by R into sine of omega t. We can see that the phase of voltage and current is same. So when we draw the phasor diagram, it would be somewhat like this. Two phasors having the same angle omega t, where one of them is V naught and one of them is IR or I naught. That is basically the amplitude of current. We'll call this as I. I naught is nothing but V naught by R. Right? Now the next concept that we are going to discuss is what happens when we connect only an inductor in an AC circuit. Somewhat like this. Only inductor. VL is the potential across the inductor. Vs is the source voltage, which is V naught into sine of omega t. So we can say that since inductor and the source are in parallel, VL equals to Vs, which is V naught sine of omega t, where VL is equal to minus L times of di by dt. Right? That is the voltage across an inductor, right? Which is equal to V naught sine of omega t, or di can be written as minus V naught by L sine of omega t dt. Integrating on either sides, we'll get I of t as minus V naught by omega L. Integral of sine is minus cos omega t, which is V naught by omega L cos of omega t, which can also be further written as I of t is equal to minus of V naught by omega L sine of omega t minus 90 degrees. The reason, V naught by omega L sine of omega t minus 90 degrees. The reason why we have written it down in terms of sine is because our voltage is also in terms of sine. So it would be easy to compare the phase of voltage as well as that of the phase of the current, right? So or else we can also write it as sorry, there is a negative sign because we are just taking the magnitudes of this. This becomes positive over here. Yeah. So current in the inductor I of t is V naught by omega L sine of omega t minus 90 degrees. What can we understand about the phase? If you put it in a phasor, you can see that the voltage of the inductor VL is like this, which is V naught sine of omega t. Whereas the current is having a different amplitude, and that we call it as I naught, which is nothing but V naught by omega sine of omega t minus 90 degrees. Since it is minus 90, the current is behind the voltage IL. This is how much? 90 degrees, and IL is equal to V naught by omega L sine of omega t minus 90 degrees. Now, when you look at this carefully, this I naught is equal to V naught by omega L. If you compare it with I equals to V by R, we can say that this omega L is equivalent to some sort of resistance called as inductive reactance. This is called as what? Inductive reactance. Called as XL, and we represent it with XL. It is nothing but omega into L, right? So we can say that for an inductor or for a pure inductor, the current always lags its voltage by 90 degrees. All right. The next concept is when only a capacitor is connected. What happens when only a capacitor is connected? Somewhat like this. Where Vs is equal to V naught sine of omega t. So obviously the voltage across the capacitor is same. So voltage across the capacitor is V naught sine of omega t, which can be written as charge on the capacitor by C, the capacitance. So Q is CV naught into sine of omega t. How do we get current? Current is nothing but dq by dt, taking derivative, which is nothing but C omega V naught into derivative of sine is cos omega t, which can be written as C omega V naught into sine of omega t plus 90 degrees. This is I of t, or V naught by 1 by omega c sine of omega t plus 90 degrees. This is I of t. Again, if you compare it carefully, I is I naught into sine of omega t, where I naught is equal to V naught by 1 by omega c. I equals to V by R form, where this represents the resistance offered by this capacitor for this particular frequency. Why frequency? Because of the term omega, which is part of it. This is called as capacitive reactance XC. So XC value is 1 by omega c, and its units are just like resistance ohms. Now, how do we put it in a phasor? If you look at this, the voltage across the capacitor VC is V naught sine of omega t, whereas current through the capacitor IC is V naught by 1 by omega c into sine of omega t plus 90 degrees. We can see that the current is leading the voltage by 90 degrees. So when we draw a phasor, if this is VC, this will be IC. Okay. By 90 degrees. Basically, this is I naught. I naught is nothing but V naught by XC. This is V naught, maximum voltage. Now we will see what happens when we have combination of when we have combination of two or more passive elements, like starting with the first one, when we have both L and R in the circuit. So we have an inductor, resistor, and the generator or the AC source. Vs is equal to V naught sine of omega. We have to understand one thing here. The current passing through the circuit or the current in the circuit will be same for all the elements, because based on the Kirchhoff's junction law, if 10 electrons are entering into a circuit, the same 10 electrons should be coming out of the circuit at the same time. So I can say that the current passing through all of them is I. This will not change. So instead of taking this, let's say the current in the entire circuit I of t as I naught sine of omega t. And voltage across the inductor is V1, voltage across the resistor is VR. This is source voltage. Now, since current is given I of t, I should be in a position to write the voltage across the inductor. Why? Because I know that in an inductor, the current lags the voltage by 90 degrees. So from there, I can say voltage across the inductor is VL0, that is the maximum voltage on the inductor, into sine of omega t plus 90 degrees, because only then current will lag the voltage by 90 degrees. And voltage across the resistor as a function of time t is maximum resistance voltage into sine of omega t. Why? For a resistor, the phase difference between current and voltage is 0. So here the phase is omega t. Over here also the phase has to be omega t, isn't it? So when we plot this, before plotting, we should know what is the maximum values, V0 and VR0. How can we get the maximum values? We have learned in the previous case, VL0 is equal to XL, that is the reactance of the inductor, into the maximum value of the current, that is I0. Similarly, VR0 is equal to resistance of the resistor into maximum current I0. Right? So substituting that, we have voltage across the inductor as a function of time t is given by XL I0 into sine of omega t plus 90 degrees. VR of t is R into I0 into sine of omega t. Plotting the phasor diagram now, we have VR of t like this, and also we have I of t like this, and VL of t is like this. So can I say this source voltage is nothing but the vector sum of these two, right? Because at any time, at any given time, the VR and VL are not in phase. So it's basically the vector sum of these two will give me the source voltage. Vector sum is nothing but the resultant. This would be Vs. So Vs is equal to VL bar plus VR bar. Right? And let's call this angle as phi. Why? Because if this is I of t, this can also be called as the source current, because Only the generator is the source for this entire current, and the current is same through all the elements. This phi is called as phase difference between the voltage and current. Right? Now, what is this value of phi? Can I say tan phi is nothing but VL by VR, or let me erase this part. Cos phi is equal to VL by Vs. Right? Now what is VL? VL is I into XL. Let's say the total resistance of this, we represent it with Z, also called as impedance of the circuit. It becomes I into Z, which is XL by Z. This cos phi is called as power factor of the circuit. This cos phi is called as power factor of the circuit. We know what is XL. XL is nothing but omega into L. But how do we calculate Z? Z is given by root over R square plus XL minus XC whole square. And I will tell you in some time how did we get this relation. Okay, or we can actually derive it from here itself. Let me clear off this page. So we have this as VL, this as VL. Let's suppose we have VC as well, this as VC. VL is nothing but I naught into XL, VC is nothing but I naught into XC. This is nothing but I naught into R. So if I just remove the I naught values, I have one more phasor which represents only the impedance of the circuit. This is XL and this is XC. XL and XC are quite opposite to each other, so it can be further simplified as XL minus XC and R. The resultant of this is Z, which is nothing but R square plus XL minus XC whole square under. This is called as impedance of the circuit. Right? The next concept is when we have capacitor and resistance in a circuit called as RC circuit. What happens? So we have a resistor and a capacitor connected to an AC voltage source. Vs equals to Vs. This value is R, this is C. And the current in the circuit is I of t. Let's say the current in the circuit is I naught sine of omega t. Our objective is to find what is VR, what is VC, and what is the phase difference between voltage and current, or what is the actual behavior of it, right? So since VR equals to VR naught into sine of omega t, because there is no phase difference between resistance and there is no phase difference between voltage and current in case of a resistor. Whereas in case of capacitor, it is VC naught into sine of omega t minus 90. Because we just learned that in a capacitor, the current leads the voltage by 90 degrees. So the phase of the current is omega t. So the phase of the capacitor should be omega t minus 90. Only then current is leading the voltage by 90 degrees. Next, what is the value of VR naught? That is the peak voltage of the voltage in the resistor is nothing but peak voltage in the conductor into R. Similarly, VC naught is equal to I naught into XC. Substituting this, we get again VR of t is equal to I naught R into sine of omega t, and VC of t is equal to I naught XC into sine of omega t minus 90 degrees. Now putting them in a phasor, what do we get? We have this as VR and this as VC, and one more phasor, this as I of t, which is I naught sine of omega t. So the resultant of VR and VC are basically the vector sum of the voltages of resistance and capacitor will give me the source voltage Vs, right, which is V naught sine of omega t minus phi, where phi is the phase difference between current and voltage. So what is the value of V naught? V naught is equal to peak current into Z, where Z in this particular case, actual formula of Z is what? Z equals to R square plus XL minus XC whole square, but here there is no inductor, so Z becomes R square plus XC square under root, right? And the phase difference and the power factor in this case is cos phi, which is nothing but XC by R. So XC is how much? 1 by omega C divided by R, which is 1 by omega RC becomes the power factor of the circuit, right? The next concept is when we have an inductor and capacitor called as LC circuit. Here we are not having a resistance. That means there is no element in the circuit which dissipates this electrical energy in the form of heat energy. What can we infer from here? We can infer that there is no actual loss of energy in the circuit. So whatever the energy is given out by the alternator or by the AC source comes back to the source after a certain period of time. What is that period and all we are going to see. Okay. So this is the inductor and capacitor LC, and this is the voltage source Vs. Let's say the current here is I of t, where I of t is given by I naught sine of omega t. Voltage across the inductor is VL, voltage across the capacitor is VC, where VL of t is equal to VL naught into sine of. Now let's observe this. In an inductor, the current lags the voltage by 90 degrees. So the phase of the current is omega t. So obviously the phase of the voltage of the inductor should be omega t plus 90. Similarly, voltage across the capacitor is given by VC naught into sine of omega t minus 90 degrees, because in a capacitor, the current leads the voltage by 90 degrees. What happens to the values of VL naught? VL naught, that is the peak inductor current, is equal to peak inductor voltage is equal to peak current in the circuit into XL. And VC naught, that is peak capacitor voltage, is equal to peak current into XC. What happens to the phasors? So VL is like this, because this is I of t, and this is VC. The net voltage would be either, if VL is greater than VC, the net voltage would be upwards. If VC is greater than VL, the net voltage will be downwards. So I can say that if VL is greater than VC, which also implies XL greater than XC, we call it as an inductive circuit, right? If it is an inductive circuit, we can say that current lags voltage. Let's say if VL is greater than VC, then the net voltage would be like this, Vs, and this is the current. So it lags the voltage by 90 degrees. The other case, that is, let me erase this part. The other case is if VL is less than VC or XL is less than XC, then it is called as a capacitive circuit where current leads the voltage by 90 degrees, right? This is what happens in case of an LC circuit. The next concept is when we have all the three elements, that is LCR, what happens? We have an inductor, capacitor, and a resistor connected to an AC source. Let's assume the current in the circuit I of t as I naught sine of omega t. Voltage across inductor is VL, this is VC, and this is VL. Now here, VR would be VR naught into sine of omega t, because the phase will not change for current and voltage for a resistor. VL naught is equal to, VL is equal to VL naught into sine of omega t plus 90, whereas VC equals to VC naught into sine of omega t minus 90, where VR naught is given by peak current into resistance, VL naught is equal to peak current into inductive reactance, VC naught is equal to I naught into XC. Let's try to draw the phasor diagram for this particular circuit. So this is VR and this is also I of t, which is I naught sine of omega t. VL would be upwards because current should lag the voltage by 90 degrees and its length is VL naught. This length is VC naught. This length is VR naught. And this is I naught. This length is naught. Now here in this LCR circuit, if voltage across the inductor or VL naught is greater than VC naught, then we can call it as an inductive circuit. Again, it's not a pure inductor, it is inductive. If VL naught is less than VC naught, then we can call it as a capacitive circuit. Again, it's not pure capacitive, it is just capacitive. Now let's look at one of the case. Let's suppose it is a pure inductive circuit. If VL naught is less than VC naught, we call it as a capacitive circuit. Now let's look at the one condition where VL naught is greater than VC naught. The net voltage across between VL and VC would be like this, which is VL naught minus VC naught. And the resultant peak voltage of the source would be like this. Let's call it as V naught. So V naught can be written as VR naught square plus VL naught minus VC naught whole square. It can also be written as, or from here Z can be written as R square plus XL minus XC whole square under root, because V naught equals to I naught into Z and VR naught equals to I naught into R. Substituting VL naught is I naught into L, VC naught is I naught into XC. This is how we get for an LCR circuit. And the phase power factor in this case, that is cos phi, is given by XL minus XC to the mod divided by Z. It is XL minus XC divided by R square plus XL minus XC whole square under root. Right? The next concept is power in an AC circuit. We'll not derive the formula, but we'll just write down the formula for it. That is, P average is given by V RMS into I RMS into cos phi. The power given out by the alternator or given by the AC source is V RMS of the source into I RMS of the source into cos of phi, where phi represents what? Phase difference between voltage and current, right? Which can also be written as Vrms is nothing but 1 by root 2 into V. IRMS is also 1 by root 2 into I naught into cos phi, which is half V naught I naught cos phi. So this is the value for P average or power in an AC circuit.